We put this paper on the archive in May 1998. It appeared in 1999 in the Journal of Pure and Applied Algebra as part of Mike Barr's 60th birthday celebration. But we put it on the archive in May 1998, and just a few days before we put it out, India exploded a nuclear device. So an article with an Indian author with a title like Nuclear Ideal Systems attracted a lot of attention, probably not quite what they expected. Anyway, I thank David and Brendan for this invitation, and I'm looking forward to getting to know the Topos Institute better. Right. So, as I said, hello, how does this? Things respond slowly. This is a talk based on work with Samson Abramsky, Rick Blute, and myself, which appeared, as I said, back in 1999, a millennium ago. And we didn't do much with it after that, but the one thing that we did do was a paper where we formalized Graham Siegel's definition of conformal field theory in terms of these nuclear ideals. So that appeared a few years later, and that was for Gordon Plotkin's Festschrift. So this was a birthday-driven piece of research. So just after a quick introduction, I will talk about compact closed categories, and in particular, the category of relations, which is kind of a paradigmatic compact closed category, or one can say, conversely, compact closedness captures the essence of the category of relations. And what Samson had been looking for was a notion of quantitative relation, which generalizes to the quantitative setting, something like the ordinary binary relation. It turned out to be a lot trickier than we thought, and we had to do a bit of functional analysis to get it into the right setting. And along the way, we, or more precisely, Rick Blute, formulated the notion of nuclear ideals. And we discovered a number of interesting examples of these. And the one that I'll talk about today are probabilistic relations. So generalizing the concept of binary relations to a probabilistic setting. There are actually two candidates for this, and I'll talk about them both. One of them fits into our framework, the other one doesn't. And I'll very briefly mention other examples before wrapping up. Okay, so let's recap. As I said, this is going to start out in a completely elementary way. Let's recap what relations are. So they're simply subsets of the set of tuples over n sets. Okay, and they're the basic ingredients of relational databases and indeed many, many other mathematical structures. So mostly we'll focus on binary relations, and we'll use the standard infix notation instead of this A comma B belongs to R viewed as a set of ordered pairs. And of course, n-ary relations can always be seen as binary ones. So we can always think by using the Cartesian product to gather things into tuples. Now, sets and relations form a category too, where to say that you have a relation from A to B simply means that you have some subset of the Cartesian product A cross B. Composition is defined in the well-known way. You need to find a mediating thing that will connect A with something, and that same thing has to be connected with a C. And if that's so, then you can connect A and C through the composite relation. I understand that the Topos Institute is founded with a view to pushing the concept of compositionality. So this is, of course, an essential aspect of relations. One can also define a trace, or in this case, what might better be called a partial trace, where if you have a common part of the domain and the codomain, you can kind of factor that out and construct a relation on the residual. So if you have a relation from A cross U to B cross U, you can existentially quantify over the U and get a relation from A to B. And that is a trace. And of course, we've seen this concept in linear algebra as well, in multilinear algebra. And in fact, there's a striking similarity, not coincidental, between the algebra of relations and multilinear algebra. An important thing is the ability to so-called repartition the interface. So you can, what you regard as input and output to a relation can be kind of easily altered and one can think of this as repartitioning the interface. Again, this is something we're familiar with also in linear algebra through the notion of transposing. So in fact, let me talk a bit about multilinear algebra. So you fix some finite dimensional vector space, and then of course you have a category with these things as the objects and the linear maps as the morphisms. And of course, you can also get a notion of multilinear map by taking simply the Cartesian product of a bunch of vector spaces and looking at maps that are linear separately in each argument. Now, of course, these multilinear maps are not linear maps. So the way you internalize this concept is by introducing the tensor product. And so you get a proper linear map from the tensor product of a bunch of vector spaces. Now, in multilinear algebra, you have matrices as concrete but basis-dependent representations of linear maps. So much so that people, and at least in the elementary linear algebra classes, tend to conflate linear maps with matrices. And of course, when you go to multilinear maps, you have higher index tensors to capture that concept. And indeed, I think it was here that the currently fashionable diagrammatic language first emerged from Penrose's diagrammatic language for multilinear algebra, which then got greatly expanded by Joyal and Street into the geometry of tensor calculus, and also by people doing topological, people doing topology knots and things like that. So many diagrammatic languages emerged. And then, of course, once the quantum computing people got their hands on it, it proliferated greatly. So now you have books by people like Bob Cook and others saying, we can do all of quantum mechanics by drawing pictures. So in the multilinear algebra setting, we also have a well-known concept like trace, which says, sorry, these should have been tensors, but never mind. If you have a map from V tensor U to W tensor U, you can, so to speak, trace out the U part of it. And there are well-known formulas, and there's a well-defined algebra of these things, and they lead to a very interesting class of categories called traced monoidal categories. Here also, one can repartition the interface by moving indices around, transposing matrices, and indeed higher tensors as well. Now, let's make all this categorical. So you have categories equipped with a multiplication, which is just a bifunctor, which is exactly this tensor product thing. It's equipped with a unit, hence the name monoidal, because it's kind of the categorification of the notion of monoid. And this tensor is associative, but of course, in the categorical setting, all these things are not equalities anymore. These are up to natural isomorphisms, such as is the unit. And there are important theorems that says any diagram constructed from the natural isomorphisms must commute. This is often succinctly summarized by saying every diagram that ought to commute does commute. And fortunately, even though there are infinitely many different diagrams that should commute, the requirement that a few specific diagrams commute is enough to guarantee that. And the theorems that guarantee that are these famous coherence theorems. Now, vector spaces and linear maps form a monoidal category with the usual tensor product. And sets and relations also form a monoidal category with the Cartesian product playing the role of the monoidal product. And it's you sometimes, but not always, in a monoidal category have an isomorphism between A tensor B and B tensor A. Every time I say one of these things, there are some other equations and things that I'm just suppressing. So in this case, we have what's called a symmetric monoidal category. Importantly, you might or might not have something called closed structure, which basically says that the morphisms can be internalized as an object. And so if a symmetric monoidal category for which every object, so if you have any old symmetric monoidal category, for every object, you get a functor, which basically says tensor with X. And there's, of course, associated morphism action as well, which is tensor with identity on X. Now, if all these tensors, all these functors constructed by tensoring with X have right adjoints, then you get what's called a symmetric monoidal closed category. Now, closed categories can be defined more generally than in the symmetric case, but it just becomes messier to state all the conditions. So I'm just going to pretend that we have one of our nice friendly categories that are symmetric monoidal closed. And of course, this adjunction precisely says you can move things around. So instead of looking at Holmes from A tensor X to B, you can look at Holmes from A to X. This is written as a lollipop. You can think of it as linear maps from X to B, internalized itself as an object in the category. Okay. Now, what do I mean by repartitioning the interface? So imagine a picture like this, where the big blob actually represents the morphism and the wires represent the object. So this is a morphism from A tensor B tensor C to D tensor E tensor F. And repartitioning the interface means these things don't really come with arrows. You can move things around like so. You can move the C from being an input arrow to an output arrow. And in the diagrammatic language, you introduce these red things called caps that allow you to essentially change the direction of an arrow. So this transposability, this ease of moving things around, is an essential part of what makes these structures enjoy the algebra that they do. So abstracting this, one comes to compact closed categories. When can one think of linear maps as matrices? And in particular, you would like to think of A lollipop P, the object of linear maps, in terms of matrices, which are basically these kinds of arrays, A star tensor B. So a compact closed category is one where for every object you have a dual object and isos nu and psi, as I have shown. And these should interact sensibly with the unit and associativity isomorphisms. And I'm afraid I've misspelled associativity, but you know what I mean. One can prove that if one has that with this dualizing object, then indeed you have an internal Hom, and that it is given by this A star tensor B. So compact closed categories are even more special than symmetric monoidal closed categories, because they actually tell you there's this nice isomorphism between the linear maps and the matrices. That's how you should think of it. And of course, the canonical example, paradigmatic example of these are finite dimensional vector spaces and linear maps. The other key example is sets and binary relations. So let me just spell out the category rel as a compact closed category. So the objects are sets, the morphisms are binary relations, the composition is, as I've said before. Given a relation R from A to B, we will write R converse for the converse relation from B to A. And the tensor product on objects is just the Cartesian product. And you can define it on morphisms. You can define this in the evident way. The unit object is any one point set. And the duality on objects is just the identity morphism, and on morphisms, the duality is just converse the relation. So this is a nice compact closed category. And I've explicitly shown in this last bullet what the new map from I to X tensor X is, X tensor X star. Okay, so all that was a very fast recap of things I'm sure everybody knows. What are ordinary binary relations? What makes them special? What's the nice algebra that they enjoy? And I was on a cube on the underground with Samson Abramsky, holding onto a strap for dear life, trying, and so to distract me, he proposed that we should search for quantitative analogues of this concept of relations. So relations are, as I said before, we compose them like that. So what are we really doing here? We're kind of hiding the middle ingredient. So there's a little b that links the A and the C. The B is linked to A through R. It's linked to C through S. And so A is linked to C through R composed with S. And we've hidden this B, which kind of serves as a witness to the relationship between A and C. Now, these relations, you can think of them as simply matrices over 0, 1. So then the idea was, okay, maybe quantitative relations should be thought of like that. So instead of maps from A cross B to 0, 1, we'll take maps into, let's say, the real numbers. So we'll have a quantitative relationship from X to Y, captured by a function from X cross Y to R, and similarly from Y to Z as a map from Y cross Z to R. And then what should composition be? Well, it should be modeled like what we did with ordinary relations. We should kind of juxtapose them and then hide the middle ingredient. And the hiding, well, what's the natural hiding operation? It would be integration. So perhaps we would look for a formula like that. Okay. Naive idea. Naive doesn't mean stupid idea. In fact, it's a very good idea. It's just that if all works well, we hope that this will also give us a nice compact closed category so that we can enjoy all the algebra that we've gotten used to from the quantitative setting. But there is a problem. If you try to define composition like that, and you try to say your morphisms are these functions on X cross Y, well, then you would expect that your identity will do something like this. You have a function called delta, and I've called it delta for a reason. So your identity map delta from Y to Y, it should have this integration property. If I integrate f of x comma y prime with delta y prime y, I should just get f of x y. But Schwartz proved there is no function like that. And that was a big problem. Well, actually, Dirac is the one who cooked up a function, so to speak, that does that job. He called it, I don't know if he called it that, but everybody calls it the Dirac delta function now. And of course, I started life as a theoretical physicist, and we took it without turning a hair. We just said, oh yeah, sure, a function that's zero everywhere except the origin, shoots off to infinity, its integral is 1, and it obeys this, and we had no problem with this. But of course, mathematicians balked at this. They thought correctly that this was, as I just described it, a frightful concept. But Dirac, if you think of it as what he said, he said, fix the math so that this thing works. And Schwartz and Gelfand invented the theory of distributions, or generalized functions, as they're sometimes called. I think independently, Gelfand and Shilov wrote a 5-volume book called The Theory of Generalized Functions. And Schwartz, of course, invented the theory of distributions during the war. Well, so what happened to us? Poor suckers trying to develop the theory of quantitative relations. So we explored the idea of using distributions and said, well, maybe it's not functions that we want these generalized functions, and that has the Dirac function in it, but there were quite non-trivial technical difficulties, and did we overcome them? So in fact, twice I proposed ways of fixing the original problem by using some techniques. So first I proposed using distributions, then I proposed using measure theory and the Dirac delta function, now modeled as the point mass at a point. Both of those ideas kind of work to give you something that satisfies the equation that Schwartz said can't be satisfied with ordinary functions. Both times we failed to construct a compact closed category. Both times we thought we had done it, Rick, Blute, and I, and we would email Samson, and within 3 minutes he would tell us an equation that was broken. So yeah, so we tried measure theory, we tried distribution theory, we failed to construct a compact closed category, and each time it failed in the same way. And then we learned this lesson that said, this is not a bug, this is a feature. And so Rick realized that there was a pattern here, and he formulated the notion of nuclear ideals and realized, in fact, that there's a well-known example of these things called, that comes from Hilbert space theory. So I will tell you this Hilbert space example, and then I will tell you a bit about what happened with the measure theory probabilistic relations example. I won't really say too much about the distributions example, just to say that there is such a thing that worked out. Okay, so roughly, in case I run out of time before getting to the punchline, I think it's always a good idea to tell you the punchline in the beginning. So there are situations where one does not have a category because the things that are dying to be the identity maps are just too singular in some appropriate sense, right? They like in the Dirac delta function case, there's this thing that just doesn't turn out to be a function. But if it were a function, it would be the right thing. So one just doesn't have a category because you don't have the identity morphisms. Nevertheless, even though you don't have a category, what you can do is embed it inside a larger category. That larger category will not be compact closed, but it will be a bona fide monoidal category. And the things that you're looking for won't be a category because identity morphisms won't be there, but there will be some subset of the Hom sets. And surprisingly, that subset forms a two-sided ideal. Namely, if you compose on either side, it will belong to your family of what we're going to call nuclear maps. But these nuclear maps will behave strikingly like a compact closed category. So it'll be like, if only we were a category, we would be compact closed. But we're not. But we do sit inside a larger thing that really is a category that's not compact closed. And we have all the nice transposing properties. The only thing we lack is the identity. So this was the kind of compromise that we reached. But in the end, you do have this property that you want, the algebraic property of being able to transpose freely. Okay, so this is kind of a summary of how the theory worked out. So let me go back to Hilbert spaces. So these are vector spaces with an inner product, which induces a norm. And of course, that norm induces a metric. And crucially, these are not any old normed spaces. They must be complete in the resulting metric. Now you can define tensor product of Hilbert spaces just as one does for vector spaces, but we must make sure that we define an inner product on this vector space product. And then we must check completeness of that inner product. Now, in the category of Hilbert spaces and continuous maps, we do have a monoidal category. I just note in passing that a map in this category, maps between Hilbert spaces are continuous if and only if they are bounded. So I will go back and forth between saying continuous and bounded. So bounded linear maps are continuous. So the category of Hilbert spaces has a star functor, just like vector spaces, an involution. And if you're looking at complex Hilbert spaces, we also have a notion of conjugation or dagger. And in fact, in our second paper, we reformulated the notion of nuclear ideals in the context of dagger compact categories, which I won't talk about here today. But if you want to see the completely equivalent formulation in terms of daggers, which are what everybody in the quantum computation world uses now, that version is also available. Okay, let's go back to this tensor product. So how is it formalized? It has a kind of universal property. So if you see Bourbaki, they will tell you this is what tensor product means. They'll say you have a bilinear map from U cross V to W. So this bilinear map here is called B. But then the tensor product is a unique vector space together with a unique map from U cross V into U tensor V. Obviously, that map bang is not a linear map. It's a bilinear map separately in each argument. But when you compose it with B, there is a unique map bang from U cross V to U tensor V, and a unique map, which we'll write bang B, such that this thing commutes. So the bilinear map has been internalized as a proper linear map from the tensor product, right? And there's a unique linear map making this thing commute. And from this, you can check that the usual definitions given in elementary texts on what tensor product means actually satisfies this universal property. And you might think, aha, this is a kind of a nice definition of a nice abstract way of talking about tensor products without going into bases and things like this and proving basis independence. Unfortunately, this doesn't work in Hilbert spaces. So one cannot internalize any bilinear map like this. So of course, if you have the diagram that I just showed you on the previous slide, if I had that in the category of Hilbert spaces, well, Hilbert spaces are vector spaces, so you indeed will get a vector space tensor product, and you will get the vector space internalized linear map from the tensor product, but it may not be bounded, i.e. it may not be continuous. So you can't do this all the time, but it does work for nice maps. And these are the so-called Hilbert Schmidt maps. So what's a Hilbert Schmidt map? So if you take any bounded linear map between Hilbert spaces H and K, then basically if you pick any orthonormal basis of the Hilbert space H, you apply F to each one of those basis members and take this norm squared and sum it. That should be a finite sum. So of course, you can also talk about Hilbert Schmidt maps from H to itself. And the first thing that you note is that, the identity map is not Hilbert Schmidt. So yes, Hilbert Schmidt maps are lovely. I just note that this is independent of the choice of basis. Let's look at this map, for example, from H cross H to H, given by, you just add the two things. So of course, on the tensor product, it maps X tensor Y to X plus Y, and then of course, you extend linearly to the whole tensor product. But this map is not Hilbert Schmidt. You can easily check that it's not bounded. And so you can't do that with this particular map. You can't do this nice internalization. And even more devastatingly, the identity map is not Hilbert Schmidt. So you can't say, oh, my category is going to be Hilbert spaces and Hilbert Schmidt maps. So here's the story that's about to unfold. Hilbert spaces and bounded linear maps, they don't form a compact closed category, but they do form a nice star tensor category, which I will define presently. The Hilbert Schmidt maps sit inside it. And these form an ideal. That's a little bit of functional analysis that I have to tell you. Now, why did we call these things nuclear spaces? So in fact, the idea goes back to Growthindieck, who discovered nuclear spaces and nuclear maps when he was trying to explain why spaces of distribution have nice properties with respect to tensor product. So of course, he was interested in Banach spaces and tensor products of Banach spaces. And he showed that there are actually 14 different tensor products, including a biggest one and a least one and so on, and thoroughly analyzed the situation. And he found out that many interesting spaces, in particular the spaces of distributions, had nice properties. And these properties, as he stated them, are highly technical and filled with details about topological vector spaces and different kinds of projective tensor products and this and that, which I don't want to say. But roughly speaking, eliding some details, it says, oh, you can think of the linear maps, one of your nice nuclear maps from A to B, where A and B are Banach spaces, is nuclear if there is an element that kind of makes it look like a matrix. This is essentially, it's not how we defined it, but it's a thing you prove from his definitions. So this is the key intuition. When can I think of linear maps as matrices? Not always. Finite dimensional vector spaces, it's so tightly coupled that we just think they mean the same thing. But in the infinite dimensional setting, no. The common spaces of functional analysis are not nuclear spaces. Spaces of distributions are, and they are often not describable by norms. In fact, you have to have a family of semi-norms to describe spaces of distributions properly. Okay, so so the only nuclear spaces that are also normed are finite dimensional ones, where everything looks nice. But as soon as you go to the infinite dimensional world, it's quite a sharp dichotomy. Okay, so let me tell you a bit of functional analysis now. So given a Hilbert Schmidt map between two Hilbert spaces and any bounded linear map from out of H2 or into H1, the composites are both Hilbert Schmidt. So the Hilbert Schmidt maps form a two-sided ideal. The space of Hilbert Schmidt maps can be itself made into a Hilbert space. And you can define a trace for bounded linear operators by invoking an orthonormal basis, you can then show that the trace is actually independent of the choice of basis. The fact that you can define orthonormal bases in Hilbert spaces is a huge boon. It's what makes Hilbert spaces so much closer to being like finite dimensional vector spaces than, for example, Banach spaces are. So this trace can be extended to arbitrary bounded linear operators, except that sometimes it might be infinite. So we'll say a map is trace class if that trace actually is finite. Canonical example of something that's not trace class, identity map. Because of course it's the ones down the diagonal, and that is a divergent sum. Trace class maps also form a two-sided ideal. One nice thing is that if you have the composite of two nuclear maps, that's always trace class. So I should also mention trace class maps are always nuclear. Nuclear maps need not be trace class. And a nice example of a map that's nuclear but not trace class is you think of them as matrices, and you look at the infinite diagonal, infinite matrix that goes 1/2, 1/3, 1/4 down the diagonal. So the sums of the squares, which is what you require for Hilbert Schmidt, does converge, but the sum by itself does not converge. For some reason, I've raised my own hand. I'm not sure why, but and I'm not sure how to lower it without getting out of full screen. So let's just imagine I'm waving at myself. Okay, but Brendan, I'm hoping somebody's monitoring the chat. If anybody wants to stop and ask me a question.
No questions yet, but we can have a quick pause and I'll try and lower your hand.
I'm not sure what I touched, but yes, thank you. Okay, so supposing C is a symmetric monoidal closed category, then you have a map from B tensor A star to A lollipop B constructed by transpose, right? Because of course you have B tensor A star tensor A to B tensor I, which is isomorphic to B, and you transpose that one, you move the A to the other side, you've got B tensor A star to A lollipop B. Good. So given a map F from A to B, we will call the map from I to A lollipop B the name of F. Okay, so it's like saying this, you can think of this as saying this matrix is the name of this abstractly thought of linear map, but that's it. We'll call it the name of F. So we're going to say that a map is nuclear. So a map from A to B is nuclear. So it always has a name. There's always this map phi from B tensor A star to A lollipop B. We'll call it a nuclear map if there's a map from I to B tensor A star such that this diagram commutes. So we'll call this P the pseudonym. I guess it should be pseudonym. Anyway, it's the pseudonym of F. So the real name of F is N of F, which lives in A lollipop B, but it might or might not have a pseudonym, which would be essentially a matrix that describes it. And the crucial point is not everything will have a pseudonym. Only the ones that do, we'll call them nuclear. And we're going to require certain preservation properties. If F and G are nuclear, then, sorry, not required. We're going to prove, one can prove these preservation properties. So the transpose is nuclear. If you compose it with any morphism, it stays nuclear on either side. And you can tensor these things and they'll stay nuclear. We're going to say that an object is nuclear if its identity map is nuclear. So of course, if its identity map is nuclear, then all its maps are nuclear because you can compose anything with its with the identity. For any symmetric monoidal closed category, if you just look at the nuclear objects, that category really is compact closed. So the nuclear objects, if you just look at them, they're exactly giving you a compact closed category. So the nuclear maps is a more liberal concept. So you have objects for which not all the maps are nuclear maps. And those are the ones that say, yeah, well, we're not exactly living in a compact closed category, but we're somehow close to it. So let me just quickly define tensor star categories. So You have an involution, which is strictly involutive and identity on objects. And we'll say such a star category is tensored if it is symmetric monoidal and interacts nicely with the tensor. And we're going to also require something called a covariant conjugate functor. So this is to handle the complex analysis possibility of conjugation. So this thing is going to commute with the star functor and has some natural isomorphisms shown here, satisfying the usual monoidal equations and some other simple equations that I'm eliding. So a tensor star category has a star, has the conjugation, and has the monoidal structure. Dagger is kind of combines the star and the conjugation in a nicer way and gives a slightly neater thing. But before we learned about daggers, we had invented this. That's why in our later paper we did everything with daggers. But in preparing these slides, I went back to the original paper, which does it in the slightly more clunky way. So now to define nuclear ideals, this is the heart of the topic. So we're going to take a tensor star category. A nuclear ideal for it consists of a subset of the Hom sets. We'll call them nuclear maps, and we're going to impose some conditions on it. This class must be closed under composition with, so it must be a two-sided ideal, closed under tensor, closed under duality, and closed under conjugation. So it has to be closed under all these things. And crucially, we want to have a bijection of this kind. There is a map theta from the nuclear maps to the Hom set that goes from A conjugate tensor B. So if F is a nuclear morphism, we can use bijection, this bijection theta and the star functor to construct various transposes. This bijection theta must preserve all of the tensored star structure. So the details are spelled out in the JPA paper, which is why I'm sparing you. The theta has to satisfy some naturality properties and a certain compactness property. And as I said before, we can define all this in terms of dagger compactness instead. So it has become common to use dagger as a functor that models essentially the adjointness of operators. So this leads to the notion of dagger compact categories. And in our later paper, we gave an alternate definition of nuclear ideals in terms of these dagger compact categories. But keeping up all these details aside, which is why I didn't really want you to stare at them too hard, the basic idea is it's not all the maps that can be transposed, but a nice subfamily of them that interacts nicely with all the structure. And crucially, the identity map is rarely one of them. I don't want to say never, because there are some special objects for which the identity map is nuclear. Those are precisely the nuclear objects. Okay, so this all seems like theory for its own sake, but it was driven by examples. And so before I go to these examples, I'd like to talk about a category that I know Evan at least is very fond of. Certainly I'm very fond of it. I'm very fond of it because I must be one of a dozen people who discovered it before we were told, oh, Lauver did that in 64 or 62 or something. But so let me talk about this category of probabilistic mappings, which isn't an instance of what I want to talk about. But still, it's too nice a category to be dismissed. So we start with the category of measurable spaces. So these are sets equipped with sigma algebras, and the morphisms are measurable functions. A probabilistic mapping between two of these measurable spaces is simply a function from X, not to Y, but to the set of probability distributions defined on the sigma algebra of Y. So probability distributions over lambda. Okay, so it's a probabilistic mapping, kind of an indexed family of measures, indexed by the elements of X. Now you can curry this and view it as a map from X cross lambda to 0, 1. And the way thinking of it in this curried form, you fix an X in X and let it vary over lambda. This is a probability measure. And if you fix a B in the measurable in the measure in the sigma algebra lambda, and let the point, the first argument, vary. This gives you a Borel measurable function on X. So it's measurable in one argument and a measure in the other. And this is set up to be composed. So composition is given by this beautiful formula. It says you compose P and Q by, so you look how this, see how this works. The composed thing should take a point from X and a measurable set C from Z. So what you do is you take this thing Q, which has a point in Y and a measurable set C from Z. But as you let this point vary, you've got a measurable function. The P thing, what you do with it is you fix the X. This gives you a measure on Y. So you've got a measurable function on Y, a measure on Y. Integration is a natural thing to do. So this integration is well defined, and you can prove that this is a nice composition in this category. You can use the monotone convergence theorem to prove associativity of composition and all kinds of other things. And these are well known in probability theory as Markov kernels. I was really thrilled when I discovered this because I thought I discovered something new, but this was known to Lauvier in 62. This was known to Michel Giry in 81, who published it as a monad, now known as the Giry monad. So she found a monad on this category, which is basically, you can think of it as a fuzzy power set. Applied to a set X, it gives you the set of all probability measures on that set. And this can be equipped with a natural sigma algebra of its own, which I will not spell out just now, or ever, in fact, in this talk. And on arrows, it just gives you image measure. So this is a nice monad, and this forms a monad. The unit is just the thing that maps each point to its Dirac measure at that point, or the point mass at that point. And the monad multiplication is some kind of nice weighted average. You can see that the Kleisli category of this monad is exactly Lauvier's category of probabilistic mappings, which he invented before monads were invented, and hence he could not present it as a monad. Okay, so this, just as the category of relations is the Kleisli category of the power set monad, this is the Kleisli category of the fuzzy power set monad, and it is therefore a nice candidate for being called probabilistic relations. And indeed, I even wrote an expository paper with that title, pushing this as the candidate for the thing that should be thought of as the category of probabilistic relations. So it has it's a very plausible candidate for that title, but it's not clear how to do transposition here. And so I sought for a different way of doing it. And of course, it lives on this, it leverages this technology, but it's a bit different. So let's go back to the Radon Nikodym theorem, which is a piece of measure theory that says, first you define this notion called absolute continuity. So we'll say a measure nu is absolutely continuous with respect to another measure mu, if when mu says a set has measure 0, nu has to agree. It could be that nu actually assigns a bigger measure when it's non-zero, but when mu says it's 0, nu can't say otherwise. So mu kind of controls the ideal of measurable of negligible sets. So the notation is like this, which, as I said, is a bit misleading because it somehow leads you to think that mu is somehow much bigger than, but it doesn't mean that at all. And the important theorem is that if this is the case, then there's a measurable function such that the new measures can be obtained by integrating this measurable function. And this is essentially unique, meaning you can have another one, but they will only differ on a set of mu measure 0, on a negligible set. And this is basically a tool to construct Markov kernels. So how do you do that? So supposing you have a measure on a product space, so you get two measures on this on the components x and y. So you've got a joint measure on x cross y. And what you do is you define the measures, these are called marginals, by saying the mu measure of a set x, of a set A is simply the vertical strip, the measure of the vertical strip. And similarly, the measure on the y-axis is the measure of the horizontal strip, like that. And I wish I had not forgotten the closing parens, but anyway, there you are. So what we defined in our paper was this category called PREL. We christened Lovier's category SREL for stochastic relations, and we call this PREL for probabilistic relations. So here the objects are not just measurable spaces, but equipped with a probability measure already. And a morphism from X to X prime is a probability measure on the product space, actually on the product sigma algebra, such that its marginals are absolutely continuous with respect to mu and mu prime. And now you can leverage this absolute continuity to construct the following. So supposing you have a probability, a probability on X, then you can equivalently get from a stochastic kernel and a probability on X, you can construct a joint probability distribution on the product space. So you can construct it on the rectangles and extend it to the whole sigma algebra easily. But you can go back and forth between distributions on the product space and these pairs consisting of kernels and measures. So given a measure on the product space, you can get by Radon Nikodym a kernel and the marginal. And conversely, if you have a marginal and a kernel, you can get a joint measure. So once you've rendered this joint measure into this kernel combination, you can compose them by taking these kernels and construct it from the Radon Nikodym theorem and composing them as Lovier did in the category of stochastic relations. So we compose as in Lovier's category to obtain a composite kernel, and then we can go back to a measure by integration. So we are essentially using those ideas, but we have to find some way of going between measures and kernels, and you can go both ways. But because you can go both ways, we now have the ability to transpose. The identity is basically the kind of what you expect, the diagonal measure. Now,
5 to the hour.
Okay. I will quickly wrap up. It's straightforward. So this was all very fast. What I want you to remember is that using these measure theoretic ideas, you can construct something that looks like probabilistic relations, and you can show that this forms a tensor star category. The nuclear ideal are the ones that have functions as densities. So in some sense, these are the things that are not very singular as measures. And it is immediate that the marginals are absolutely continuous with respect to these. And of course, there's always the usual hassle about almost everywhere uniqueness, but it doesn't matter very much. It turns out that these things exactly define a nuclear ideal in this category PREL. So PREL is not a compact closed category, but it is a monoidal star category, and it has a nuclear ideal. These are the ones that can be treated as transposable probabilistic relations, the ones that have nice functions as their densities. So the nuclear ideal corresponds to the original naive idea of using real valued functions as relations. And the fact that we don't have the identity, it's too singular to be a function, but we can realize it as a measure. And that gives us the outer context in which we have a proper category. So the category we get by including such measures is not compact closed, but the original functions do form a nuclear ideal. So there are other simple examples one can construct from injective partial functions. It's easy to make it into a tensor star category. It turns out the nuclear ideals are obtained by looking at functions whose domain consists of at most one point. So that gives you a nuclear ideal. Using distributions, you can use the Dirac delta function as the thing that serves as the identity. We had to do some work to make this work, but it can be done in that context. I don't want to dwell on this right now, but the important point is that with distributions, you can do things that you can't do with measure theory, like differentiate distributions. Okay, so we developed another tensor star category based on these generalized functions and showed that the functional versions of these, because functions also describe distributions by simply integrating with respect to the function, these give you precisely the nuclear ideal. So it's the same phenomenon. You use functions as your quantitative relations. You can compose them by integration. The identity doesn't live there, but it does live in the larger space of distributions. And that can be formalized as the tensor star category. It turns out conformal field theory is all about cobordisms. So TQFT was formalized by Atiyah in a more sensible way after Siegel's definition of conformal field theory. So if you read Siegel's notes, there's a footnote that says, yeah, I know this is not a category, deal with it. He doesn't quite say it like that, but essentially that's what he says. So we actually showed that his category was actually a nuclear ideal inside a nice star tensor category. So that star tensor category was the category of Riemann surfaces where you compose by gluing things along circles. And what happens is that the identity morphism wants to be just a one-dimensional circle, but that's not a Riemann surface. It's become too thin to be a Riemann surface. It's become too singular. So it's the same phenomenon. The thing you want to be the identity is dying to be there. It's just too singular to be there. Okay, good. So let me wrap up. So there are many natural examples of nuclear ideals in mathematics. There's a beautiful theory due to Rick, where he took this. I've always just given you examples of saying the identity is too singular, but he kind of made a real theory out of it using a thing that I don't know called shape theory. So this, I think he never published, but it's a tech report on his webpage. One of the things that I've often wondered, is there a nice diagrammatic language for nuclear ideals? Because basically in compact closed categories, what makes the diagram language work is the ability to bend morphisms. So here you have to somehow say there's some morphisms that are rigid and can't be bent and others that are bendable. But I've never really worked out a nice theory of a diagrammatic language for these nuclear ideals. Now it's well known that compact closed categories and so on are great for finite dimensional quantum mechanics. Maybe these things would be good for formalizing infinite dimensional quantum mechanics using this nuclearity concept. Right, so maybe I will stop here and let people ask questions.
Great. Thanks, Prakash, for a really beautiful story. I'll open the floor to questions. I guess you're still sharing your screen, but there's a bunch of applause and icons.
Yes, I can see that. I think Sergey has a question.
Appreciation. But yeah, Sergey has a question.
Hi, Prakash.
Hi.
Thank you for a very clear explanation of this paper. I mean, I'm familiar with that original paper, but I have never seen you speaking about it.
By the way, are you in Germany now?
Yes. In the
At Max Planck.
Yeah. And the city of Erlangen program.
So your question.
Yes. So I've been wondering, I mean, do I see it right that most of the stuff that you presented, that goes back to that original paper? Because yes. You then mentioned the other one, 2007, right?
Yes.
And I wonder how big is the part from there is in the talk, because I think I'm going to read that paper next, perhaps.
So that paper, so it's one thing to give these talks hiding the details. The details can be quite difficult, which is why I highlighted them. So in that second paper, nearly all the stuff is trying to do integrals on Riemann surfaces to make sure that certain things compose nicely. It's nice to say things should compose, and I'm a big fan of, somehow I didn't join the compositionality club as a cop, but I am a true believer in the importance of this concept. But often you have to do a lot of intricate details to prove that things compose properly. And much of the detail in that new paper about conformal field theories is about doing the right integrals to make sure that things work out the right way. But it's essentially about gluing Riemann surfaces together. So in cobordism, there's no analysis to be done, right? It's all topology. You do things and deform them. You get this nice category of cobordisms, which is still a rich enough structure in its own right, but it's incredibly much more intricate in the case of Riemann surfaces.
So, but it's basically an application of this theory from the old paper to yet another class of examples, right?
Yes, yes.
I mean, roughly speaking.
Yes, well, I wouldn't say it's an application. It's more like another instance of.
Instance, yeah.
Yeah. So I think Andreas had a question next, and then Peter.
Yes, I enjoyed that very much.
Thank you.
One thing that came to mind while you were talking about sort of a small part, a small well-behaved part inside a bigger thing that is well-behaved in a different sense, and that tends to include things, singular things like distributions and so on. This is reminiscent of what happens in some treatments of Hilbert space theory, where the small thing is a Hilbert space, and the bigger thing with distributions is what they call a rigged Hilbert space.
Oh God, yes.
Is there a connection here, or is it just my imagination running wild?
There could well be a connection. I have not explored it. I remember rigged Hilbert spaces from my physics days, because this is another example of a thing that physicists happily did.
Right.
And so the canonical example.
The Hilbert space is L2, but we have plane waves and we have delta functions and all of that. That's in L2. Never mind.
Yeah. Well, yes, exactly. So it's got a basis, but the basis vectors are not in the space. So,
Right.
So that's the rigged. So in fact, this word is quite interesting, rigged, because it sounds like you're cheating in some way. But then physicists will always say, no, rigged as in equipped for sailing. So
Yes.
So it's actually an interesting idea. I don't know how well formalized mathematically the theory of rigged Hilbert spaces is. I think it's probably quite well formalized by using operator value distributions. Is it? So I don't know if it's an example of this phenomenon, but it's actually a very tempting example to look into. Thanks for reminding me that it exists. I think I must have blocked it out because I didn't want. I'm sure proving it will be quite a lot of work, if it really is. But yes, it's a beautiful, similar situation.
Okay. Thank you.
Peter Hines, I think, next. At least these are the hands I can see. I don't know if I'm seeing all the hands.
Hello, Prakash.
Hi, Peter. How lovely to see you.
Good, yeah, good to see you. Thanks for a very nice talk. So I've got a suitably vague question, which is in compact closed categories, of course, there's a close connection between the compact closed structure and categorical Frobenius algebras. Now, a paper from Samson and Chris Hoynen a while back showed that there wasn't really any obstacle to defining Frobenius algebras in the infinite dimensional case.
Yes,
so
I
was essentially wondering, sort of, given a sort of framework of nuclear ideals and such like, essentially, how do you go from there to Frobenius algebras?
Yeah, I don't know. So to be honest, I haven't been working, for the last 20 years, I've been doing probability, and now God help me, I'm doing machine learning. So there are natural questions like this that I wish I had looked into, but I haven't. And ironically, I'm visiting Chris Hoynen right now in Edinburgh. That's where I am, by the way. I'm based in Edinburgh for 3 months. And I have not explored that question, but it is a natural and interesting and hardly vague, Peter. I would say it's a very sharply and incisive question, sharply worded and incisive question. I should think about it. But yes, there is no obstacle to defining Frobenius algebras. Where are you, by the way?
I'm in York at the moment.
York! Wow, not so far away.
No, just down the train line.
Okay, so there's another question.
So
should I ask mine?
Yes, please.
Okay, yeah. To get a feeling for compact closed categories, is there an analogy to the concept of compactness in topology?
I don't think so, but maybe the experts, the category experts, Valeria, is there I don't think so.
I agree. I don't think so either, myself.
Okay, great. Thank you.
Valeria, you have your hand up.
I do have my hand up. Hello, Prakash. Nice to see you.
Nice to see you
I
too.
was watching it on YouTube because I had problems with the connection with Zoom, which was very broken, but very beautiful, long story. I really enjoyed it. My question is about why did you, why haven't you kind of so far thought about trying to find the opposite direction? You're trying all the time to think about how to make the category compact closed. My that's not suggestion, is what I would like to see is, you know, what can we get just using the stars or just using the symmetric monoidal closed categories? Because then you would have this other kind of logical thing about full intuitionistic linear logic as perhaps a model for your stuff. So, I mean, did you ever think about it, about kind of not having the compact closed, but just saying, where can I find this extra structures of the, I mean, maybe that's what Rick Blute did on this 2007 manuscript that you mentioned. But
I don't think so. Anyway, my interest was not in finding models for a specific logic, but rather understanding the specific structures. So I was interested in this notion of quantitative relations, and I was saying, what does it look like? And
right.
Indeed, it was a bit of a fixation to say it must be compact closed. You know, this is somewhat typical arrogance of young people. They think that things should be the way they want them to be and not the way they really are. So, but yes, we eventually learned that it is not compact closed, and this is what the structure is. We did think about things like geometry of interaction, and that geometry of interaction construction plays a role in our conformal field theory paper. But we didn't try to find specific models of linear logic with it, because I think, you know, star tensor categories are very weak things, right? That they don't have, yeah, they're very, and the nuclear things are pretty strong, maybe too strong, but they are the structure that's there. So what you're suggesting is also an interesting thing from a different direction. You can say, I mean, the paradigm is I have this well-behaved thing living inside this less well-behaved thing. And you could have asked questions like that, like, do I have models of intuitionistic linear logic living inside something that's a bit wilder and just a, you know, maybe just a star tensor category? And we didn't look for them because I wasn't really looking for models of linear logic. But you're the expert on models of linear logic, aren't you? You must have seen examples like that.
Well, I think, you know, it gives me a little bit of a feeling, but of this idea that whenever you have something where you have internal homes, you can always think about the double negated objects, and those would be the ones that would give you your compact closed category. So, you know, and I kind of personally try to think more about the things that are infinite dimensional and hence are not compact closed, but simply symmetric monoidal closed. And, you know, it's a question of, to my mind, at least, it's a question of where you're trying to, what you think is more important? Is it the internalization of the internal home, or is it really a duality, a full duality? And so, you know, but I loved it. So I'm kind of definitely going to go and try to follow the calculations and see if my way of looking at it kind of does get me something interesting. That
well, if you do that, I'll be thrilled, because as I said, I kind of abandoned this whole line of research doing, not because I thought it was not interesting anymore, but I just got caught up in, well, in probability. I kept thinking, I'll have done everything I want to do with, you know, Markov processes in the next couple of years. And for the last 25 years, I've been thinking in a couple of years, I'll be done. Markov processes seem to have a life of their own. They don't give up so easily.
Well, thanks. It's been a very engaging question time. I think it's a good time to bring formal proceedings to a close, though. So I'll, you know, wrap things up. But thanks again. Let's thank Prakash once again for an amazing seminar.
Thank you. Thank you all. I'm very sorry Dave couldn't be here. I hope he gets well soon. And what is that?
Yeah.
You're such a lovely audience. I'd like to take you home with us, but but it is pretty wonderful that some of you can be in California and I can be in Edinburgh, where it's already dark, and Sergey is in Germany, and people are all over, and we can still communicate and interact.
It's really nice indeed. So at this stage, we often